Hello, class 12. So, we are going to deal with power in AC circuits today. LCR was the last kind of alternating current circuits. Now we are going to discuss about power in alternating current circuits. Now let us start with the most general one, considering an AC. What have I written? It's not AC circuit. Considering an LCR circuit. Okay, the most generalized kind of circuits, alternating current circuits. So considering an LCR circuit, we've already seen that this is VL quack VC, or VL minus VC if VL is greater than VC. So this is that. So this is the effective voltage, and phi is the angle between the effective voltage and the current in LCR circuit. And we've seen if VL is greater than VC, then the voltage leads the current by a phase angle of phi. So basically in LCR circuit, there is some phase difference between voltage and current. If VC is greater than VL, then the current leads the voltage by a phase angle of phi. So basically there is some difference, okay? And in this case, let us consider that the instantaneous value of voltage is V0 sin omega t, and we are considering that the current lags behind the voltage by a phase angle of phi. Or so to say, we are considering VL is greater than VC here also. And of course, the phase angle phi is given by tan phi is VL quack VC divided by VR, which is equal to XL quack XC upon R. So we know this. Therefore, the instantaneous value of the power, is given by instantaneous value of voltage times the instantaneous value of the current. Okay, I have denoted the instantaneous value of current by small I, so let me rather write small I over here. So small I VI. So this is equal to V0 sin omega t into I0 sin omega t minus phi. There is a phase difference of phi between the current and the voltage. So then after, it's simple mathematics. So this is V0 sin omega t, and what we are doing is we are expanding this thing, sin omega t minus phi, in the form sin A minus B. Sin A minus B is sin A cos B minus cos A sin B. Alright, so we've expanded that. Now what we do is we multiply by this sin omega t, both the terms inside the bracket by sin omega t, and we get sin square omega t cos phi minus sin omega t cos omega t sin phi, of course. Now this second term inside the bracket, what we do is we multiply and divide by 2, the second term, and we get 2 sin omega t cos omega t. Now what is 2 sin theta cos theta? 2 sin theta cos theta is sin 2 theta. So in this case, sin 2 omega t divided by 2. So that is the only change here in the last line. Okay, that is the only change in the second term inside the bracket. Alright, now there are some things that we need to understand in here. So for that, let me erase the upper part. Okay, I hope I can do that. So you can quickly pause the video and copy if you wish to copy. So I'm erasing this thing. So I'm erasing this part also. And I'm erasing the phasor diagram also. We don't need the phasor diagram. Okay, now what we do is we consider one complete cycle of alternating current. One complete cycle of alternating current. And what we do is we are plotting omega t along the x-axis, the phase or the phase angle, and let's say this is sine A, so this is sine 2 omega t, radiation of sine 2 omega t. Now for one complete cycle of alternating current, we see that the upper half is exactly equal and opposite to the lower half. So this is the variation of sine 2 omega t we are plotting. Okay, so for one complete cycle, the upper half of sine 2 omega t is equal and opposite to the lower half. So to say, for one complete cycle, the value of sine 2 omega t is equal to 0. Understood? So for one complete cycle, sine 2 omega t being 0, the whole second term rather, is 0 over here. And looking at this sine squared omega t, now from trigonometry, I almost said Tigo, okay? So from trigonometry, we can write cos 2 omega t is equal to 1 minus 2 sine squared omega t. This is what we can write. Alright, now for one complete cycle, considering one complete cycle of a cos wave variation now, cos omega t. Cos omega t, of course, is not this. Alright, it's like sine wave and cos wave are basically one and the same thing. Only thing, it depends on where it's starting. Alright, so cos wave is something like this. Okay, so up to here is one complete cos wave because it starts from 1, cos 0 is 1. So for one complete cycle, this one complete cycle of cos wave, this half plus this, okay, these are positive cycles, is equal to the lower half over here. So for one complete cycle, cos 2 omega t, okay, cos 2 omega t is also 0. So to say, this left hand side is 0, and therefore we can write sine squared omega t is half. Alright, so for one complete cycle, sine 2 omega t we've seen is 0, likewise cos 2 omega t is 0, but sine squared omega t for one complete cycle is equal to half. Okay, so can I erase this? This is rough work actually, but don't forget, this is 0, this is equal to half. Alright, so I'm erasing this part. For one complete cycle, sine 2 omega t is 0 and sine squared omega t is equal to half. We've seen this. So therefore, what does the expression for power now look like? So power is equal to, this whole term is 0 like we've already discussed. So this is half. So I can write half V naught I naught into cos of phi. Alright? Which can be written as, or rewritten as, P is V naught by root 2 into I naught by root 2 into cos phi. Now what is V naught by root 2 and I naught by root 2? When we started alternating current, we've seen that Vrms is equal to V naught by root 2. Likewise, Irms is equal to the peak value of the current divided by root 2. Okay, so this is Vrms and this is Irms. So let me erase this. Therefore, we get the power is Vrms Irms into cos phi. So this is the expression for power in case of an alternating current circuit. Now if you understand this, if you know this expression, you can derive the value of power for any kind of an alternating current circuit, be it resistive circuit, inductive circuit, capacitive circuit. Alright? And this cos of phi, it has a name. It's called the power factor. Cos phi is what is called the power factor. Okay, now see, from this expression, can I erase the lower half? Of course I can, isn't it? So I believe you've paused the video and already copied that. So if it's a resistive circuit, okay, let me write number 1 for resistive circuits. For resistive circuit. This is the expression for LCR circuit, don't forget. So for resistive circuit, what do we know? We know the phase difference between current and voltage is 0 degrees or 0 radians. Okay, so what is cos 0? Cos 0 is 1. Therefore, power in case of a purely resistive circuit is Vrms into Irms. So this is the same as in the case of direct current, so to say. Because in case of direct current, we have seen the power is voltage times the current. Alright, so it's like the same as in the case of direct current for resistive circuits. Now, for inductive and capacitive circuit, pay attention over here. Alright, so we need to look into that. For inductive and capacitive circuit, the phase difference between the voltage and the current is pi by 2. So cos pi by 2 is 0. Alright, so number 2, I'm including for both capacitive and inductive circuit. And inductive circuit, what do we have? Phi is pi by 2. So therefore the power factor becomes 0 because cos pi by 2 is 0, and thereby the expression for the power is 0 itself. For both capacitive and inductive circuits, remember. Therefore, in a purely capacitive and inductive circuit where there is no resistance, okay, we see that the power is 0. Or so to say, in case of purely capacitive and inductive circuit, there is no energy dissipation in the circuit, although, mind you, current is flowing in the circuit. So this kind of a current flowing in a circuit, in which case there is no energy dissipation in the circuit, or the value of the power is 0, then such current is called wattless current. Watt is the unit of power, okay, so such a current is called wattless current. So I hope I can erase this. So you can write the definition of wattless current yourself. Wattless current. Sometimes you get 1 mark question, define wattless current. The current flowing in a purely inductive or capacitive circuit which has no resistance, of course, in which case there is no energy dissipation in the circuit because the power is 0. Such a current is what is called wattless current. Alright, so this is all for this video, class 12. Thank you.